Hello everyone, my name is Marco Comunità and I am a PhD researcher in the Center for Digital Music at Queen Mary University of London. Today I want to talk to you about our ICASSP paper, Modeling Black Box Audio Effects with Time-Varying Feature Modulation, a work in collaboration with the authors listed on the screen. Audio effects are tools employed by engineers and musicians central to shaping the timbre and dynamics of sound. Among these, analog effects, especially vintage ones, are often appreciated for their sonic characteristics, although they are not easily accessible, can be expensive, and require regular maintenance. Therefore, digital emulation of audio effects is an area of active research, which has led to the development of many commercially available plugins. Although the design of such emulations requires expert knowledge and can be time-consuming. This motivates the use of neural networks to automatically create emulations of audio effects. The process typically requires a dataset of recordings, which are played through the audio effect, all the while recording the output signal. Then we can take a neural network and train it to generate the same output we recorded from the reference device. Deep learning approaches have seen success in modeling a range of effects, although most existing work focuses on nonlinear effects with behavior on relatively short timescales, such as guitar amplifiers and distortion pedals. Modeling behaviors on longer timescales has proven challenging and so far less investigated. There has been some work on dynamic range compression, which shows behaviors over long timescales, but is only moderately nonlinear. In this work, together with compression, we tackled the challenge of modeling highly nonlinear time-varying audio effects like fuzz distortion. These circuits are characterized by attack and release time constants in the order of hundreds of milliseconds up to several seconds. I would like to give you an example that shows why fuzz is challenging to model and why it is not just a type of distortion. In this first plot, we show a sinusoidal wave whose amplitude changes over time from -20 to -3 dB. If we process it with a typical distortion circuit, the result will be similar to the one shown in the second plot. We can notice the amount of gain as well as the clipping, but not much more than that. If we now send the same signal to a typical fuzz circuit, the difference is quite evident. The fuzz has a much higher gain, causing it to clip at much lower input amplitudes. But, more importantly, we have a clear time-varying behavior that is function of the input signal. Also, we can clearly notice the attack and release time constants for increasing and decreasing input signal. If we now zoom in, the differences are also evident in terms of waveform. While the distortion circuit shows a symmetrical clipping only moderately dependent on the input amplitude, the fuzz is characterized by asymmetrical clipping whose duty cycle is strongly dependent on the input amplitude and the function of time. If we listen to the clean and distorted signals, you should be able to clearly perceive the dynamic behavior of fuzz. To capture these complex dynamics, we propose to incorporate time-varying feature modulation into existing temporal convolution networks. This allows us to model input-dependent behavior over large timescales, which in turn enables superior performance across a range of fuzz and compressor effects without increasing the receptive field of the main network. We also show that simply scaling width, depth, or dilation factor of existing architectures does not result in satisfactory performance. We demonstrate this by implementing a custom analog fuzz circuit with attack and release controls. Finally, we share the trained models as a real-time VST plugin. For our purpose, and similarly to previous work on distortion effects modeling, we adopt a feed-forward wavenet architecture, which we refer to as gated convolution network. The GCN is composed of n blocks, each one containing m gated convolution layers. Each layer is made of a dilated one-dimensional convolution followed by a gated activation. The outputs from each layer are summed through a one-by-one convolution to produce the final output. Starting from the GCN architecture, we integrate temporal film layers into each gated convolution layer. Using recurrent networks, temporal film layers modulate the intermediate features of a convolutional model over time as a function of the activations at each layer, which allows to leverage long-range dependencies in the conditioning signal. Given a sequence of activations Zn, we split the sequence into blocks of B samples along the sequence dimension. For each block, one-dimensional max pooling is applied to downsample the signal by a factor of B. Then, an LSTM produces a sequence of scaling and bias parameters that are used to modulate each channel individually. The output of each temporal film module is sent through a one-by-one convolution and combined with a residual connection Xn and sent to the following layer. To evaluate our proposed method, we compare it against state-of-the-art recurrent and convolutional architectures proposed for the tasks of guitar amplifier and distortion effect modeling. We prepare datasets of processed electric guitar signals and evaluate the ability of the models to capture behavior over different time constants using our custom analog fast circuit, as well as the digital compressor available from the Spotify Pedable library. Further experiments and thorough evaluation are available in the paper, and we invite you to check it out. In these figures, we show the multi-resolution STFT loss for baseline and proposed models for different time constants and model sizes. We can notice how the proposed model, indicated as GCN-TF, outperforms LSTM and GCN baselines for the task of fuzz modeling, regardless of the time constants of the circuit. Although this is not always the case for compressor modeling, where LSTM performs slightly better for shorter time constants. It is also interesting to notice how baseline with shorter receptive field, namely GCN1 and GCN3, which both have a receptive field of around 50 milliseconds, tend to perform worse than baselines with longer receptive field, namely GCN250 and GCN2500, having a receptive field of respectively 250 and 2500 milliseconds. On the other hand, the opposite is true for models with temporal film, where models with short receptive field achieve better results. For details and results of all the experiments, we invite you to check the paper. That concludes this talk, and thank you for joining. I hope you find this interesting. You can find some audio samples on the web page associated to the paper, and you can find the code on our repo. Also, feel free to try out the VST plugin available on GitHub or by downloading the Newton plugin. If you are interested in following more of our work, you can follow us on Twitter. Thank you again for your interest in our work.